Hi everybody, this is Mrs. GA, and today we're going to be learning about the properties of logarithms. Before we get started with the lesson, I have a quick warm-up for you guys, so please pause the video and give this one a try. All right, go ahead and check here. So just remember, logarithms define exponents, so we're essentially saying 16 to what power is 1/2. So to cause that reciprocal, the exponent should be negative, and then you'll see that 2 is actually the 4th root of 16, which is why it's a rational number. Same idea here. For this one, I think it's actually easier to write 36 as 6 squared, because hopefully you recognize that 216 is 6 cubed. So if you do the cube root of 216, it gives you 6. So think of 1/3 as the exponent, but then it's 6 squared, so you still have the 2 in the numerator. And then last here, again, to get the reciprocal, our exponent should be negative, and 7 is actually the cube root of 343. So to do a cube root, we have a rational exponent. Okay, so today we're going to be working on the properties of logarithms that you see here on this slide. So the first 3 are really just kind of common sense. We call them definition-based properties. You don't actually need these to know that. For example, log base b of b to the power of m is m, because you're saying b to what power is b to the m? Well, this must be the exponent. But whenever essentially you see that the bases match, you can simplify it to whatever you see up in the exponent. Here, b log base b of 1 equals 0. Of course, b to or any base to the power of 0 is 1. So anytime this number is a 1, your logarithm will equal 0. Again, technically this a definition-based property, but you can figure this out with common sense. And then here, if the bases match, well, the exponent must be 1, because b to what power is b? Yeah, 1. Now, these are the properties we're going to focus more on today, because they're not as common sense based. So the first one is the product property of logarithms. So if you have the logarithm of a product, okay, so this number here is a product, you can actually rewrite this as the sum of 2 different logarithms. Now they would have the same base, but it's the log base b of m plus the log base b of n. Notice that this doesn't work for, there's no such thing as the sum property of logarithms. So you can't say that the log base b of m plus n is anything. There's no property for that. There's no way to expand that out. But if you have a product here, you can actually write it as the sum of 2 different logarithms. Same thing for a quotient. If you have the logarithm of a quotient, you can write it as 2 separate logarithms that are a difference. Again, notice that that's not a property for a difference. Okay, you cannot expand this into 2 separate logarithms. It must be a quotient here. The power property of logarithms tells you that if you have log base b of m to the power of n, you can actually take that exponent and you can actually move it right out front. So it's a really unique property of logarithms, can be very useful. Or you could always go backwards. If you see a coefficient out front, you could always move it up here to the exponent of this term. And then last is the change of base property, which we've talked about before. We really just use this primarily to help you plug something into your calculator, so you could change any base logarithm to be, you could change it to whatever base you want. We'll probably be using common log or natural log, because again, we really only do this to help us get a decimal approximation of our logarithms. But technically, you can change any base logarithm into the quotient of 2 logarithms with a new base. So this number goes to the top and the base goes to the bottom here. All right, so we're going to practice using our properties to help us condense these expressions. So we're going to express each expression as a single logarithm and then simplify if possible. So here we have the difference of 2 different logarithms. So we can use our quotient property, and we can write it as a single logarithm. That is a quotient of 27 and 81. And now here we can see if we can simplify this. So we're essentially asking 3 to what power is 27 over 81. So it will definitely help us to simplify this. This is 1/3. So we see that the exponent must be -1. So that's the value of this logarithm. All right, let's try this next one. So here I have a sum of two different logarithms, which I can condense into a single logarithm that is the product of 1/25 and 625. And now to see if we can simplify this, I'm first going to say let's simplify what's in here. So we could say log base 5 of 25. We know that this just means 5 to what power equals 25? Oh, this logarithm is equal to 2. And last here, we can actually use the power property, and I can take the 3 that's in the numerator, or in the exponent here, and I can actually just move it right out front. So we can say 3 times the log base 2 of 32. And we know that this, the logarithm, if we evaluate that, should be 5, because 2 to the power 5 is 32. So we just do 3 times 5, which is, 3 times 5, which is 15. So you can see here we use that power property, here we use the product property, and here we use the quotient property. All right, let's try a few more together. So we're going to do the same thing. We're going to try to condense the expressions into a single logarithm. So we're going to be using, for part A, a combination of the product and quotient. And what I typically like to say is any logarithm that is negative, those values will end up in the denominator, and any logarithm that is positive, those values end up in the numerator. And we are just going to write it as a single logarithm. So just start by writing the word log one time, and then looking at the expression. Again, anything that was positive logarithm will end up in the numerator, so x squared and y cubed. And then anything that was in the denominator, that is negative, a negative logarithm, will end up in the denominator. So it's a combination of the product and quotient rules, and we could simplify this a little bit into xy squared. And that's as much as we can simplify, so we are done condensing. So let's look at this next one. They are all natural logs, so I'm going to write natural log a single time. And again, any logarithm that was negative just means you're using the quotient, so those will end up in the denominator. And any logarithm that is positive, that value ends up in the numerator. So a is the only thing that's going to start in the numerator, and then we have a squared times b to the 5th times a cubed times b to the 8th. So both of those are negative logarithms, so it's essentially like using the quotient property for both. Now we can kind of simplify what's going on here. So we have a over a to the 5th times b to the 13th. And we can leave this as 1 over a to the 4th, b to the 13th. And there you have it. So it doesn't matter what order the sum or difference is written in, right? You could actually move these around because you're just adding or subtracting, but I just like to say anything that is a negative logarithm ends up in the denominator, anything that's a positive logarithm ends up in the numerator. Okay, go ahead and pause the video and see if you can give these two a try on your own. All right, go ahead and check here. Here we can use that power property, so you can take the exponent 3 and move it right out front. And we can evaluate the log base 4 of 64. It's equal to 3, then you multiply that by the 3 that was out front, and you get 9. And then for part B, we can use that quotient property, so a single logarithm where you're taking the quotient of these two numbers, so it becomes log base 8 of 8, which is 1. All right, so now we're going to practice doing the opposite. We're going to take a single logarithm and expand it out as much as possible using those same properties, but kind of the reverse of those properties. So the first thing I see here is that this is a product, so we can expand it into actually 3 separate base 3 logarithms. So log base 3 of 3, and it will be the sum of all of them. So log plus log base 3 of a squared plus log base 3 of b cubed. Now from here we can simplify a little bit for this first one, log base 3 of 3 is just 1. And then to help us even further expand, we can use that power property and take this exponent and move it out front. So plus 2 times log base 3 of a. And same thing here, we'll put this out front. Plus 3 times log base 3 of b. And this is as expanded as we could get. Okay, for the next one here, I'm going to be using a combination of the product and the quotient. So remember, any term that is in the numerator will give you a positive logarithm. So we'll have log base 5 of 2 plus log base 5 of x squared. And anything that is in the denominator will give you a negative logarithm. So minus log base 5 of 5 minus log base 5 of y cubed. This will, of course, just be equal to 1 or negative 1. So we can put that out front, and we can just evaluate this. And then we have plus log base 5 of 2. Here we could use our power property, plus 2 log base 5 of x minus 3 log base 5 of y. And here it is fully expanded. So again, this was kind of to practice using those same properties, but in the reverse order. All right, I have one last example for you to try on your own. So please pause the video and hit play when you're ready to check. All right, so one thing to notice is that this entire term, the 2xy squared over 5z, is being raised to the power of 3. So you could raise each term inside to the power of 3. So you could have 8x squared y to the 4th over 125z cubed. Or you can take this 3 and move it out front from the beginning, and then expand from here and then distribute the 3 in later. And if you have negative log base 7 of 125 instead, it means the same thing. So that would be fine as well. All right, that is all for today's video. Thank you so much for watching.